Hey guys, I'm Craig Enders and I appreciate you tuning into the Blimp video channel. In this video, I'm going to talk about something called pattern mixture models. You'd use a pattern mixture model for a missing not at random process where the unseen score values might be related to missingness. That's a really different assumption than our usual one, which we call missing at random or conditionally missing at random. As a couple examples, first think about a clinical trial designed to decrease smoking or drinking behavior. It could be that the intensity of one's usage actually dictates whether or not they're going to continue with the trial. As a second example, in an educational study, a student's decision to opt out of high-stakes testing might be related to their underlying achievement levels. Before we get started, I want to thank the Institute of Educational Sciences for all their support and point you to the project's webpage. You can download Blimp from the same website. I have a pair of videos on missing not at random analyses, one for the selection model and one for the pattern mixture model. Both incorporate an explicit model for missingness, but they do that in different ways. Suppose our focal analysis is a regression model where X predicts Y and Y has missing data. Let's assume that it's plausible that a person's unseen Y score is related to non-response, even after accounting for the observed data in X. The dark blue rectangle labeled M sub Y is a binary missing data indicator that codes whether Y is observed. This binary variable equals 1 if Y is missing and 0 if Y is observed. A missing not at random process says that even after we control for a model's observed data, there's an association between the unseen Y scores and missingness. Selection models and pattern mixture models introduce this association in different ways. The selection model on the left incorporates an additional regression equation where Y predicts missingness. The model can also include direct pathways between the predictor variables and missingness. The pattern mixture model on the right instead reverses the role of the missing data indicator, which now functions as a predictor variable in the focal model. The model can also include interaction effects where the association between X and Y differs by missing data pattern. In this video, I focus on a pattern mixture model where the missing data indicator is a predictor in the focal model. To make the illustration more concrete, I'll use data from an educational study. The data file includes assessments of broad reading in first grade and ninth grade, and it also includes teacher ratings of behavioral symptoms and learning problems from first grade. I'll use a linear regression analysis where the three continuous measures from first grade predict ninth grade performance. This is our focal regression model. Our usual assumption about the missing data process is something called missing at random or conditionally missing at random. This assumption requires that the unseen score values are unrelated to whether or not a student has missing data in ninth grade. Essentially, all the reasons for missingness are contained within our model's observed data, and we don't need the unseen score values to get accurate parameter estimates. But suppose that we're concerned that this assumption might not hold. It could be that whether or not a student has test score data in ninth grade is related to their underlying achievement. The pattern mixture model allows this possibility by incorporating a missing data indicator as a predictor into the model. This is a path diagram of a basic pattern mixture model. I added a dark blue dot on the dependent variable in the path diagram to represent the model's intercept. In the equation, this is beta 0 com. When we have a dummy code in a regression, the intercept is a predicted value or mean for a subgroup coded 0. In this case, the intercept represents the mean for the subgroup of students who have data in ninth grade. They have a score of 0 on the misread 9 dummy code. Next, let's consider the slope coefficient for the missing data indicator. The slope represents the ninth grade mean difference for students with missing data. A pattern mixture model is essentially like a multiple group model with the missing data patterns as the grouping variable. However, those subgroup means aren't really our main interest. What we really want is an intercept or mean that averages over the missing data patterns. To do that, we just need to take a weighted average of the group-specific means. The population level intercept estimate that we really care about, which is beta 0 in the equation, pools the pattern-specific means. The weights, which are the pi's in the equations, are just the missing data pattern proportions. So the equation says just to add the group means together after weighting them by the proportion of students in each pattern. The resulting intercept is a population level estimate that averages over the distribution of missing data. I want to start by fitting a model that just has the missing data indicator as a dependent variable, because this is going to illustrate some important functionality for getting those missing data pattern proportions and doing the weighting. The path diagram on the right is an empty regression model for the missing data indicator. In the syntax, the transform command creates a new missing data dummy code called misread9. This variable equals 1 if the score is missing and 0 if the score is observed. I define this variable as categorical on the ordinal line. In the model section, the missingness model features that missing data indicator as the dependent variable. By default, this is a probit regression with an underlying latent response variable. Notice that I'm labeling the intercept coefficient mismean. I'm going to use that intercept to compute the missing data pattern proportions. In the parameters section, I define two new parameters called pmiss and pcom. Pmiss uses the grand mean of the probit model to get the proportion of students with missing data in 9th grade, and pcom is the proportion of students with complete data. Here's the entire Blimp script highlighting the parts we just looked at. I explained the other commands in different videos. For the rest of this video, I'll focus on the changes to the model and parameters sections as we build out the analysis. This is the regression summary table for that binary missing data indicator. The intercept, which is the grand mean of an underlying latent response variable, is used to get the pattern proportions. The point of this empty model was to get the proportions of students with missing data in 9th grade. These new parameters show up in a table labeled generated parameters. We can see that 17% of the students are missing their 9th grade reading scores, and about 83% have that data. Now that we've established the missing data indicator part of the model, let's merge that with our focal regression analysis. The path diagram shows the focal regression model with the missing data indicator as an additional predictor. The model command consists of two parts. One part is for our focal regression, and then a second part of the model is for the predictor variables. As a bit of housekeeping, I'm using labels in the model section to reorder the summary table so that the focal model appears first and the supporting predictor models appear next. Looking at the focal model, I label the intercept and group mean difference as B0com and B0diff. I'm going to use these labels to compute the group-specific means and then average those together with the missing data pattern proportions. Next, I label the intercept in the missingness model just like I did in the previous script. In regression models, we usually assume that predictors are correlated, so the final line introduces all possible correlations among the predictors, including the missing data indicator. Because the missing data indicator is binary, its correlation with other variables is on the latent response variable metric. Remember that model is not exactly what we want because the intercept and the group mean difference represent subgroup parameters. I attached labels to the intercept and group mean difference, and we can use those to compute the population level intercept estimate. In the parameters command, I add another line of code that computes the weighted average intercept estimate. B0com is the subgroup mean for students with complete data, and then B0com plus B0diff is the group mean for students with missing data. We're almost there, but I've omitted a really important detail, and that's that this model's not actually estimable right now. One of our two groups has no data in 9th grade, so there's no way to estimate that group mean difference. Going back to our model, remember that B0com is the mean for students with complete data in 9th grade, and the B0diff slope is the mean difference for students with missing data. We can't estimate that mean difference because the 9th grade data are completely missing for that subgroup. The literature describes several strategies for achieving model identification. I'm going to show a simple strategy that uses a standardized mean difference effect size to determine that group mean difference parameter. This strategy is going to allow us to stress test our model parameters by essentially controlling the strength of the missing not at random mechanism. So for example, suppose that we thought that students with missing data might have scored lower in 9th grade. We could ask the question, what do our parameters look like if those students differed by 1/5 of a standard deviation at 9th grade? How would my model parameters change if those students were 1/2 a standard deviation lower, for example? Looking at the figure on the right, we have the mean for the complete cases, but we don't have the mean for the missing cases because we have no data. We're going to specify that mean difference on a standardized metric. Looking at the parameters command, I specify a Cohen's d effect size of -0.20, meaning that students with missing data in 9th grade scored lower by about 1/5 of a standard deviation. If I know the group mean difference on a standardized metric, I can easily solve for the raw mean difference using a simple equation. To get the raw mean difference, I just multiply the effect size by the standard deviation of the dependent variable. In the parameters section, I compute a new parameter called B0diff based on that expression. Appending .totalVar to the reading variable's name gives me the variance of the 9th grade reading scores, and then taking the square root gives me the standard deviation. The value of B0diff is going to get substituted into the focal model as a constraint. We no longer need to estimate the parameter because we've fixed it at a deterministic value from the effect size. This is the summary table for our focal regression model. Remember that the intercept and the mean difference are not the parameters of interest. Rather, these parameters define the subgroup means. A standardized mean difference of 0.20 converts to about a 3-point difference on the raw metric. The generated parameters table now shows the pooled intercept estimate that averages over the missing data patterns. The strength of the pattern mixture model is that we get to control the strength of the missing not at random mechanism. For example, I could stress test my model parameters by increasing the size of the standardized mean difference effect size to 0.35. This allows me to conduct a sensitivity analysis that examines the stability of my main conclusions over different assumptions about the missing data process. All we need to do in the Blimp script is simply change the effect size. Here I'm saying that students with missing data in 9th grade are lower by a little more than a third of a standard deviation unit. The B0diff parameter in the line below that transmits the effect size to the focal model. The regression summary table shows that we induced a bigger gap between the two groups, with the raw mean difference in 9th grade now exceeding 5 points. Finally, we can invoke an even more extreme scenario where students with missing scores in 9th grade are 1/2 of a standard deviation lower. The regression summary table shows an even bigger gap between the two groups, with the raw mean difference now equal to about 7.7. What I just did was essentially turn up the missing not at random knob on our focal model. We can view those sets of results as a sensitivity analysis that describes how our model parameters change over different assumptions about the missing data. The table summarizes the focal model parameters from 4 different analyses. The purpose of the sensitivity analysis is to see whether the main conclusions were consistent across the 4 models. Essentially, is the model robust to different assumptions about the missing data process? The leftmost columns display the results from the default conditionally missing at random assumption, and the remaining columns display the pattern mixture model results. The changes to the model primarily affect the intercept, which in this case represents 9th grade reading performance. The mean is about 67 when we assume a conditionally missing at random process. In the most extreme case, assuming that the missing 9th grade scores are about 1/2 a standard deviation lower changes the mean by a little more than a point. I would describe that as a fairly minor change because a point or so difference is only about 1/5 of the posterior standard deviation or Bayesian standard error. If we thought that the slope coefficients also differed by missing data pattern, we could introduce interaction coefficients into the model. It's important to emphasize that there's no way to adjudicate these differences. There's no way to determine which of the 4 models is more correct because all of them make different assumptions about the unseen score values. It's fine that the results weren't perfectly consistent, they just simply reflect different assumptions about the missing data process. As a reporting strategy, we could talk about the default missing at random results in the body of our paper, and then use an online supplement to describe the sensitivity analysis. That wraps up our quick introduction to pattern mixture models for missing not at random processes. I limited this to a fairly simple model where the two groups differed in their mean, but we could also have more complicated models where the regression slopes also differ by missing data subgroups. From the help menu in the graphical interface, you can access the Blimp user guide, and there's an entire chapter devoted to missing not at random analyses. That chapter includes several pattern mixture models for both single and multi-level regressions. Thanks again for tuning in, and I hope you check out other videos.